we can start. Yeah, and people will join a bit later. Okay, so let's start. Welcome, everyone. Today, I'm very happy to introduce Simeon Hellerman from Kavli Institute in Tokyo, who will tell us about precision correlators at large R charge. Please, Simeon.
Oh, so thank you. I'm extremely excited for the invitation. Well, anyway, I'm looking forward to telling you about some stuff that my collaborators and I have been working on over the last several years, about, I guess 5 or 6 years now, maybe, yeah, 6. So the talk is about the simplification of, well, and by the way, I have a kind of introductory part giving some background, which I'll start with, and then I'll segue into the more like precision supersymmetric part of the talk as we go on. But generally, it's about the simplification of otherwise strongly coupled quantum systems in the limit of a large quantum number, which I'll refer to generically as J. And by otherwise strongly coupled, I mean strongly coupled outside of any simplifying limit where the theory becomes semi-classical for other reasons, or possibly in such a simplifying limit, but with the quantum number taken so large that the system behaves differently than you might have expected, despite it being weakly coupled. So there could be a situation where large quantum number overwhelms and counters the weak coupling parameter. So the primary question of such a talk is, well, is this even a subject? Simplification at large quantum number? The answer is yes. And in some sense, it's a very old subject. Many examples have appeared in the literature going quite far back into the past. You can go arbitrarily far back, really. But recently, there have been a number of groups focusing on systematizing this point of view and applying it more broadly. So we can go back as far as the ancient Greeks with the atomic hypothesis, then Bohr's correspondence principle, skipping ahead a couple of millennia, large spin in the hadron spectrum, noted by Regge and then others, the so-called macroscopic limit of Deutsch and Schrednicki, and then maybe more recent old stuff, n equals 4 super Yang-Mills at large R charge, the BMN limit and various people who followed them, the large spin expansion in general CFT from light cone bootstrap, as studied by Komargatsky, Zhiboyev, and Fitzpatrick, Kaplan, Poland, and Stuffin, and Aldai and collaborators. The large spin expansion in hadrons, studied by several groups, including myself, Ian Swanson, John Maltz, Shinsuke Maeda, Simon Karen Hewitt, Zor Komargatsky, Arne Sever, Sasha Zhiboyev, and other paper by Sever Zhiboyev. And well, just then more modern history, a large charge expansion in generic systems with abelian global symmetries, myself, Watanabe, Rufford, and Orlando, and then many other papers followed in what I'll sort of call the modern large quantum number era. And then specifically what I'll be getting to today, large R charge in supersymmetric theories, especially with vacuum manifolds and exact chiral rings. And in addition, there's been just so much explosion of interesting work in this area in the last few years. I can't do justice to it all, but here are some interesting papers. I encourage you to check out all of them if possible. The goals of the large quantum number expansion overlap very much with the goals of the conformal bootstrap, namely to learn to systematically and efficiently analyze quantum field theory in quantum field theories, usually conformal field theories that have no exact solution in terms of explicit functions. So here I am at the Integrability Journal Club saying that the goal is to analyze non-integrable theories. But that's what we're doing. We'd all like to know, what does theory space look like for generic theories and generic amplitudes? Most theories aren't integrable. We need to learn how to attack them in general circumstances. And direct numerical bootstrap methods, though remarkably efficient, power law and the number of operators, still break down in various extreme limits, because the number of operators grows exponentially with the dimension or central charge or whatever other quantum number. But what's interesting is that all known extreme limits appear to have simplifying behaviors in ways that currently can't be explained directly by the numerical bootstrap. In the case of large spin in a single plane, this limit has been analyzed within the bootstrap itself. But for other quantum numbers, this really isn't the case. So for instance, there's no known analytic bootstrap method to attack the case even of large spin in multiple planes in 4 or more dimensions. And the same is true for internal global symmetries of various kinds. Now, in many cases, such limits are accessible to some new kinds of effective field theories in regions where these extreme limits, where bootstrap methods slow down. And as we'll see, there's also an excellent agreement for some predictions where the two methods overlap. But so where does this leave us? What do we hope to accomplish? Well, we could, I think for purposes of this talk, I'll say we're just focusing on the most modest possible goal, which is to translate EFT behavior into bootstrap terms, say what it means for CFT data, and like operator dimensions and OPE coefficients. But of course, one could aspire to more grandiose goals, but I haven't made any progress on those, so I'm not going to even talk about them. So the simplest example to consider is the conformal Wilson-Fisher O2 model at large O2 charge J. So the canonical question one can ask about large quantum number there is, what is the dimension, so called delta sub J, the dimension of the lowest operator at large charge J? And so translated via radial quantization, you can ask, what is the energy of the lowest state of charge J on the unit 2 sphere? So the normalization group analysis reveals the low-lying large charge sector is described by an EFT of a single compact scalar chi, which can be thought of as the phase variable of the complex scalar phi in the canonical UV completion of the O2 model. So the leading order Lagrangian of the EFT is really incredibly simple. So this is one of the first times you get a look at how simple this limit is. The large charge sector is described by an effective Lagrangian of the form some unknown coefficient times grad chi cubed, and that's it. At leading order, that's the entire, at large charge leading order, that's the entire effective Lagrangian. It's the second simplest Lagrangian you can possibly write down. So free massless scalar is the simplest possible conformal theory you can write down. That's grad phi squared. Well, this is grad chi cubed. You cannot get any simpler than that without making it free. So the coefficient B isn't something we know how to compute ab initio, but the simple structure of this EFT has sharp and unexpected consequences. And as we'll see, we can pin down B, the coefficient B can be pinned down very well by other means. The immediate consequence of the structure of this EFT is that the lowest operator is a scalar of dimension that goes C sub 3 halves times J to the 3 halves, where C sub 3 halves has some simple expression in terms of the coefficient B. So the leading order EFT predicts more than just the leading power law, because quantum loop effects in the EFT are suppressed at large J. So the EFT can be quantized as a weakly coupled effective action with effective loop counting parameter J to the minus 3/2.
Sorry, could I ask a question?
Yeah, please.
Yeah, sorry, just to go back, I guess, should I worry that there's an odd number of derivatives appearing? I guess
well,
I'm more used to, for bosons, seeing an even number of derivatives.
Why do you want, I mean, should you worry? No. Why?
That's
I mean,
what
it's Lorentz invariant, it's conformally invariant, it's fine.
Okay, but it isn't sort of parity invariant, is that the idea?
It's parity invariant because of the absolute value.
Because of the absolute value.
Yeah, I mean, it's by grad chi cubed, I mean, grad chi squared to the 3/2 power.
Yeah, yeah.
So it has all the symmetries that grad chi squared would have. It has everything.
Yeah, okay.
I mean, it can accomplish that because it's non-analytic at chi equals 0, but that's a feature, not a bug.
Okay. So can I just to get a feeling, because I guess I've never thought about such a term before. Suppose I coupled it to a normal quadratic term and treated B as a perturbation.
Well, you don't want to do that. I mean,
I know. But could I imagine that this is somehow some fixed point of a flow of such a theory that I start with, or?
I mean, it is the fixed point of a flow, but not grad chi cubed isn't in the microscopic action. It's just an effective theory.
Yeah, no. I know. I'm sorry. So sure. I'm just trying to get an idea for where such an effective theory
where it comes from.
In a
I mean, it comes from. I mean, we sort of explained it in the paper, but it comes from where it comes from is. So the Wilson-Fisher model flows to something which at large field looks like it has a sextic potential.
Mm-hmm.
Then you integrate out the radial mode of a theory with a canonical kinetic term and a sextic potential. Integrating out the radial mode then gives you this term.
Okay, that helps.
Right, because you get a squared grad chi cubed, a squared grad chi squared, where a is the radial direction, chi is the angular, the phase direction, and then the a to the 6th, you eliminate a algebraically, and it gives you this thing.
Yeah. Okay, thanks.
So just to confirm, that's specific for O2 model at the moment, right?
Well, the other ON models work similarly, but there are more they're more angular variables. So I mean, the higher ON models have been also analyzed, but they're a bit more complicated. They have a lot more degrees of freedom in them. But they also have this kind of cubic thingy, but they have other stuff too. I mean, if you want to learn about the ON models, there's a beautiful series of papers by Orlando Reffert and Alvarez Gomez, and some other people.
Thanks.
So I mean, this simple EFT predicts a lot. It predicts, the entire spectrum of low-lying excited primaries. So the low-lying excited primaries have dimensions, spins, and degeneracies, which are those of a Fock space of oscillators of spin L with L greater than or equal to 2. So the propagation speed of the chi field, you can just work out from the Lagrangian, and it's equal to 1 over square root of 2 times the speed of light. So the frequencies of the oscillators are omega sub L is 1 over root 2 root L times L plus 1 for L greater than or equal to 1. Now the L equals 1 oscillator is there, it's in there, but exciting it only gives descendants. The leading order condition for a state to be primary is that it has no L equals 1 oscillators excited. So for instance, the first excited primary of charge J always has spin 2 and dimension equal to the ground state with charge J plus square root of 3, plus some, subleading large J corrections.
So just to link to something we know, like an n equals 4 similar limit would give something like Landau-Lifshitz model as effective Lagrangian
Well, so for n equals 4, I mean, again, it depends on the rank because whatever. But for n equals 4, like SU2 super Yang-Mills,
No, I
it's
mean
just
like planar.
oh well, plain. That's a whole different story. I mean, everything I'm talking about here. So in the planar limit, you get something like BMN, but everything I'm talking about here is going to be the limit where the quantum number is larger than every inverse coupling of the system.
All right. Okay.
So larger than n, larger than g. Other limits where j is large but less large than some other things, those have been analyzed by people like BMN. And then also more recently, a beautiful paper by, I forget, Shota Komatsu and a couple of other, I think Simone Jambi was in there. I'm sorry that I'm forgetting the authors. It was very recent. It was just like last week. But yeah, I mean, many other limits can be analyzed, but there's been beautiful work on them, but I've mostly focused on, and I'm going to focus here on the limits where j is much larger than everything else. But yeah, for supersymmetric examples, which I will get to, the effective theory is the vacuum manifold effective theory. So we'll see plenty of examples of those. So then subleading terms can also be computed. So those depend on higher derivative terms and the effective action with powers of absolute value grad chi in the denominator. And those counterterms have a natural hierarchical organization in J. So at any given order in derivatives, there are only a finite number of such terms. And as a result, at a given order in the large J expansion, only a finite number of those terms contribute. And since they're far more observables than effective terms, there are an infinite number of kind of theory-independent relations among terms in the asymptotic expansion for various observables. So for instance, the first subleading term, so the gradient cube term is the only term at order j to the 3 halves, and then there's only one other term with a non-negative power of j, and it looks like this: a grad chi times the Ricci scalar plus 2 grad of grad chi squared over grad chi. Now, in particular, there are no terms in the EFT which scale as j to the 0. And the result of that is that the j to the 0 term in the expansion of the operator dimension is calculable. It's not renormalized by anything, and it's independent of unknown coefficients in the effective Lagrangian. And specifically, the formula for the asymptotic expansion of the operator dimension with lowest with charge j looks like something times j to the 3 halves plus something times j to the 1 half minus 0.093726 and so forth. So this is independent of all the other things we don't know, up to terms vanishing at large j. So also an infinite series of negative powers. That number, though, is very interesting. Okay. So the universal term doesn't have any fudge factors or adjustable parameters. Given the identification of the EFT, that value is universal and absolute. And then similar predictions have been made for OPE coefficients as well by many interesting papers on this EFT by the EPFL group. Now, so many questions one gets frequently asked. You might think that there's something like weird or inconsistent or uncontrolled about a Lagrangian like grad chi cubed. So you might ask, isn't this singular? Isn't it weird that it's a non-analytic functional of the fields? That's kind of why it's so unfamiliar. And it is non-analytic, but the non-analyticity is irrelevant. You're not supposed to use the Lagrangian around chi equals 0 or around constant chi. You're supposed to expand around the large charge vacuum, which at large j is a classical solution that's linear in time with gradient mu. Mu is the chemical potential. And then the expansion into Vev and fluctuations carries a suppression of mu to the -1 or more for each fluctuation, and mu scales as j to the 1 half. So by the way, the Nambu-Goto action is exactly the same kind of effective theory. Outside the critical dimension, it's still a perfectly well-defined effective theory. You just don't expand it around point-like string states. So then you can ask, wait, isn't this theory, non-renormalizable? Aren't loop corrections incalculable? And the answer is no, loop corrections are calculable. You always take the UV cutoff, you treat the theory as an EFT and you take the UV cutoff parametrically higher than the infrared scale, which is the size of the sphere, and parametrically below the UV scale, which is the square root of the density. So then loop divergences go as powers of lambda cubed over rho to the 3/2, which is much less than 1 in this limit, and they're proportional to non-conformal local terms, which can be subtracted off to maintain conformal invariance of the EFT. So the UV divergences are perturbatively calculable, and you subtract them off anyway. So then you can ask,
could I ask, so expansion goes in the powers of 1 over j, right?
1 over j to the 3/2.
Oh, that's right. Oh,
And
okay.
that's a difference between the O2 case and the supersymmetric case. In the supersymmetric case, 1 over j is the loop counting parameter, and in the bosonic, the generic bosonic case, it's 1 over j to the 3/2. But it also depends on the space-time dimension. But in 3 dimensions, it's 1 over j to the 3/2. And for supersymmetric theories with vacuum manifolds in any dimension, it's 1 over j.
Just in the formula you show for delta, it was what, the j is 3/2 and 1/2 and then constant.
Right. Sorry. Yeah, I should say there are 2 types of corrections. Good point. There are 2 types of corrections. There are corrections. Good. Thank you. There are corrections which are in fact powers of 1 over j, which come from, those are like classical corrections. They come from higher derivative terms in the classical action of the EFT. Whereas the loop corrections come in inverse powers of j to the 3/2. So yeah,
So
that's important.
this constant is one loop constant then.
Yeah, this constant is a 1 loop term.
Okay.
Right.
And the second term is correction to the Lagrangian kind of classical
That's right.
correction.
That's right. And where you have a loop term but no correction to the Lagrangian, that's where you get universal calculable terms.
Sorry, this constant, does it depend on the rank of the Fourier symmetry group? Or?
Well, yeah, if I remember correctly, this constant is also the same in the higher ON models.
I see.
The universality class is different, but the 1 loop constant is the same. The other degrees of freedom have dispersion relation that don't contribute at 1 loop. I mean, they contribute in other ways, but yeah, I think this constant is actually the same for all the ON models.
Thank you.
You're welcome. So, and then as usual in EFT, the counterterm ambiguities of subtraction correspond 1-to-1 with terms in the original action allowed by symmetries. So the counterterms don't spoil the universality. And then at that point, many people say, wait, are you saying that every CFT with a conserved global charge has this exact same asymptotic expansion at large charge? And no, there are certainly other CFT with global symmetry that are not in this kind of large charge universality class. So for instance, free complex scalars are at a different universality class. Free complex fermions are in a different universality class. Theories with parity breaking, parity asymmetric theories in 3D are in a very different universality class that's been analyzed by a group containing Cuomo, Delacroix, and oh boy, I'm sorry, there's another very distinguished author I'm forgetting, and I'm going to get I'm going to regret that, but it's in the references in the slides. Sorry, whoever it is, though. But anyway, so there are other large charge universality classes, even in 3 dimensions.
Where is ABJM in that?
Oh, ABJM is a very different universality class. Of course, it is one. It's very different because it has many flat directions. It has infinitely high rank. And again, ABGM is a limit where you're not even taking J to be the largest quantum number. So it's in this general family of things, but it is very different.
Number for ABJM.
Sorry, for ABJM at large R charge. I mean, there are many different large R charge limits you could take, but it's it has large supersymmetry and.
I see. So if I took the obvious BMN limit, would it be 0?
Would what be 0?
That number that's 0 that you showed us.
Oh, for any theory with a vacuum manifold, the leading power law is J to the 1, and it's not just the leading power law. It's exactly J to the 1 with no coefficient, with no higher terms, because it's BPS saturated.
I see. So I need to stop thinking about those examples.
Yeah. Oh, I'm sorry. Even in ABJM, I think even in N equals 4, there are choices of U1 in the R symmetry group that don't have supersymmetric states in them. They're like non-BPS U1s. So for those, actually, I think the story is more similar to the O2 model, but I think those haven't been analyzed. I'm not sure what universality class they're in.
U1s in the ADS directions?
No, I mean, they're U1s in the sphere directions, but there are non-supersymmetric U1. There are, in fact, generic U1s in the SO6 or in N equals 4 or the SO8 in ABJM, or SO whatever in ABJM. Generic U1s don't preserve a killing spinner.
I don't understand that. Aren't all U1s fully equivalent?
No.
What?
No.
I mean, yeah, well, why not? I can always rotate. Pick a U1 and rotate. Like a global SO6. And
No. Yeah, you can rotate to a carton, but not all. I mean, not all vectors in the.
Oh,
and some of them don't preserve any killing spinners.
Okay. So you take, yeah.
Okay. Analyzing the non-supersymmetric charges in N equals 4 or in ABGM might be extremely interesting, and I think nobody has done it.
Thanks.
Anyway, there are many other interesting universality classes, but I don't want to. I'm gonna get too bogged down if I talk about all the interesting things. So among the most tractable universality classes are large R charge in extended superconformal theories with moduli spaces of supersymmetric vacuum. So the simplest case is the N equals 2, D equals 3 superconformal fixed point with 3 chiral superfields, no gauge symmetry, and superpotential X, Y, Z. Okay, so without loss of generality, you can consider the X branch. Now, the X branch has a coordinate ring spanned by X to the J for J greater than or equal to 0. And these BPS scalar chiral primary operators are the X branch part of the chiral ring. And the dimension of Xj, as I just mentioned, is exactly equal to its R charge J and protected from all quantum corrections. So in this case, the formula for the dimension is just boring. Okay, it's just J. That's it. The dimension of the lowest state is not that interesting to compute. Now the formula for the
could I ask, so the
yeah.
excitations above the state, they could be less boring, right?
Oh yeah, and I'm about to get to that. And so yeah, I'm gonna say what they are. The analysis was done in a paper by myself, Watanabe, and Maeda. But yeah, the second lowest primary, unfortunately, is still also boring. It lies in a protected scalar semi-short representation with only 12 Poincare superpartners, and as a result, its dimension is also protected. It's J plus 1. Now, we'd still like to see that explicitly in a large J expansion, and we'd also like to be able to compute the non-protected large J quantities like the third lowest operator dimension, and also like OPE coefficients and things like that. So let's talk about what the effective theory is. The effective theory describing the lowest state or the low-lying states in general is just the moduli space effective action appearing in the same role as the gradient cubed theory in the O2 model. So unlike the O2 model EFT, the leading action here is just free, and that's why the leading term goes as j to the 1 rather than some other power. And so here we're going to trade in x for a fractional power of x treated as a superfield. Phi is x to the 3/4, and the leading Lagrangian, the leading superspace Lagrangian is just phi dagger phi, and then there are higher derivative d terms in the action. So to compute the lowest, to compute operator dimensions, just quantize the theory around the lowest classical solution with given large J on an S2 spatial slice again. So here the classical solution is just V times e to the I mu t, where mu is 1/2r and V is root J over 2 pi r. And here one difference is that the chemical potential is determined by supersymmetry, by the BPS bound. So now the results of the direct diagrammatic quantization are as follows for the first and second lowest states. For the lowest state, the BPS chiral primary, the direct diagrammatic quantization gives you 0 times J, gives you J plus 0 times J to the 0 plus 0 times J to the -1 plus 0 times J to the -2 plus 0 times J to the -3, and then a 3-loop term which we didn't compute that goes as J to the -4. Presumably it's 0. Then at 2 loops you get J plus.
Sorry, that's a sequence of zero. Do you use them to fix some relative constant as the effective Lagrangian? Or Lagrangian, you don't correct it at this order.
So I actually haven't written down the correction. We're going to write down a first D term correction in a second. Right. So these loops come from quantizing the Lagrangian I haven't written down yet. Sorry, but well, I mean I can skip ahead to it. It's this. It's this plus a supersymmetric completion. Then the second lowest state has from direct diagrammatic quantization, its dimension is J plus 1 times J to the 0 plus 0 times J to the -1 plus 0 times J to the -2 plus 0 times J to the -3, and then an uncalculated J to the -4 coefficient at 2 loops, which again presumably is 0, confirming the predictions of supersymmetry to the order we can calculate. And the third lowest primary is a non-BPS scalar with dimension J plus 2 times J to the 0 plus 0 times J to the -1 plus 0 times J to the -2 minus 192 pi squared kappa J to the -3. And then 1 loop terms we didn't compute. So kappa is the leading interaction term in the EFT, and the form of the leading interaction term, it's a D term consisting of a 4 derivative bosonic component that looks like grad phi to the 4 over phi to the 6th. And kappa, we don't know what it is, but it obeys a superluminality constraint that forces it to be positive. So we know that the first non-protected operator dimension gets a contribution of order J to the -3 with a negative coefficient of unknown magnitude.
Sorry, in this effective action, are there no corrections?
Oh yeah, there are plenty of higher terms as well, but they're suppressed by higher powers of J.
So to get to 3 loops, you don't need to know them? Still?
To get to 3 loops, you don't need to know. Yeah, I mean, just because the supersymmetric effective action is, has many fewer terms. The derivative expansion starts at, you can see it starts at like 4 derivatives. So you just, it's just because of the magic of supersymmetry, the superspace measure suppresses things dimensionally a lot. But yeah, I mean, past this point, you get more and more high derivative effective terms again.
But at this point, where do you see supersymmetry before you start computing loops? At the level of this effective Lagrangian?
Oh, well, I mean, it's a D term. Yeah, I guess I didn't write the superspace form of the D term, but you know, this
Okay,
term
if it's super, it's
has an explicit.
supersymmetric.
Yeah, but this term has an explicit superconformal form,
So
which
effective Lagrangian keeps kind of all the symmetries of the initial one. It's only when you expand around the classical you lose them.
that's right. That's right. In fact, you know, we were very lucky because the like this bosonic term had been written down a long time ago, and it had been supersymmetrized, fully supersymmetrized only very recently, like a year before we wrote the paper in a nice paper by Kuzenko. So the explicit supersymmetrization had not existed for very long, but it does exist. We wrote it down on the paper, we wrote it in components, but then you know, Kuzenko gives a nice derivation of the superspace form.
Is it actually guaranteed that effective theory has the same symmetries as the initial one? Because
well, they're there, but they're spontaneously broken. But yeah, I mean, it has them. It has them
you break them
explicitly.
only by the background.
Yeah, you break them only by the background, not by the dynamics. That's right. I mean, the term, the full term with all the fermions and everything. This isn't the full term. You know, there are also fermions. There are curvature corrections, all sorts of things. We wrote down in the paper. I'm not writing it on the slide, but you know, together that full set of terms has a manifest, explicit superconformal.
This is like a theorem that effective Lagrangian should only have it broken spontaneously.
Oh, I don't know, but I mean, if it's a theorem, but I mean, it's the easiest way to do effective theory. You mean, could there be other terms that that are allowed that don't have manifest symmetry or something? I mean, I don't know.
Because like in principle, the initial problem you're solving breaks the symmetry from the beginning. Then you're lucky to have some Lagrangian which describes the spectrum around, but
I mean, I don't know what you mean by breaks. It breaks it spontaneously. I mean, it's it's spontaneous breaking. It's like the chiral Lagrangian, right? The chiral Lagrangian has an explicit SU3 times SU3, but the vacuum breaks it. It's literally the same situation.
Yeah, well, but I always kind of a bit confused. Why should it be this way? It doesn't look like it's guaranteed necessarily because the problem you're solving doesn't have those symmetries anymore.
I mean, it does. There are ward identities that say the symmetry is obeyed, even if the state doesn't preserve it.
Yeah, but the symmetries could lead you outside the kind of approximation where this is valid, the effective theory, right? In principle.
Well, I mean, I don't know.
All right. But
I don't think they do. But yeah, I mean, for theorems like that, I don't know. I guess like CCWZ, you know, or all the other papers on the subjects, you know, develop these things. But I think you just write down all possible terms obeying the symmetry. Anyway, it's more fun to compute quantities which are both non-trivial in the large J expansion and checkable in principle by exact supersymmetric methods. So one nice example is the 2-point functions of chiral primary operators in 8 supercharged theories. And the technically simplest class of examples are the chiral primaries spanning the Coulomb branch chiral ring in n equals 2 theories in 4 dimensions, in the special case where the gauge group has rank 1. But by the way, how many minutes in are we? I can't see the clock because I'm full screen.
Well, more or less now it will be.
Okay. Should I break here or should I go on?
Well, it is a question of few minutes, so as you prefer.
Well, if there is some natural point nearby, maybe
yeah, okay, maybe nearby. I can yeah, a little bit further on. I will. So yeah, there are various examples. The example I'm going to mostly focus on is n equals 2 super QCD with a gauge group SU2 for flavors, but there are many other examples. And what's nice about large quantum numbers, we can treat Lagrangian and non-Lagrangian theories all on equal footing. So the Coulomb branch chiral ring in a rank 1 theory is spanned by powers of a single generator, which we'll call O sub delta. The chiral ring in rank 1 is always freely generated. And again, at large charge and radial quantization, these just correspond to classical solutions on the sphere where the Coulomb branch scalar gets a VEV proportional to root J over R. So for Lagrangian theories, the generator curly O is just trace phi squared, and delta equals the dimension of the generator is 2. But for non-Lagrangian theories, delta can take other values. So again, to write the large J effective action, we can work in terms of an approximately free effective field, which is just the 1 over delta ith power of curly O sub delta. So again, the leading order action is just free. And it turns out that the first subleading term is a term controlled by the anomaly. It's controlled by the Weil A anomaly. And the interaction term is a coefficient I'll call alpha times, it is formally a full superspace integral for n equals 2, but it's a full superspace integral that's really secretly an F term because the integrand of the full superspace integral isn't really single valued. So this is just it's actually an F term. It's just a kind of convenient shorthand for a true F term. And then alpha is proportional to the Weil anomaly mismatch. It's 2 times the A anomaly of the underlying CFT minus the A anomaly of the effective theory on the abelian effective theory on the Coulomb branch in certain sort of commonly used units for the A anomaly. So this interaction term, this slide is wrong. I'm sorry, I was corrected recently. It was first written down by Grusaro, Rocek, and I think Siegel, and then not long after, Dine and Seiberg somehow wrote it down again. And its bosonic content is the famous West-Zumino term for the Weil A anomaly that was used by Komargodski and Schwimmer to prove the A theorem in 4 dimensions. And that's why alpha is proportional to the A anomaly mismatch. And one other remarkable fact, this is special to rank 1 theories, is that this anomaly term is the only F term which is non-zero on conformally flat space. So on S4 or on flat space or on the cylinder, this F term is the only F term in the action. So there are many higher derivative D terms, but they don't affect the quantities we'll be computing because the quantities we're computing are protected. So the EFT is therefore very simple. It's just the free kinetic term plus this anomaly term plus higher D terms. And for quantities insensitive to D terms, like the ones we'll be calculating, this simple 2-term effective action can be quantized meaningfully, and it gives unambiguous answers to all orders 1 over J, in 1 over J perturbation theory. And any purely F-term dependent observable has a large J expansion that's uniquely determined by the anomaly coefficient alpha and nothing else for a 1-dimensional Coulomb branch of an n equals 2 gauge theory. So the set of observables we'll be talking about are the Coulomb branch correlation functions. So correlations of the nth power of this chiral ring generator, 2-point functions of those. So the way to study them at large charge are to treat these insertions as being so big that they're effectively classical sources. So you take them up into the into the action as delta function supported sources. Right. So the new action is the EFT action plus the source action. And we'll define Z sub n as the partition function with sources, where the sources are the nth logs of the nth powers. So this quantity is scheme dependent and dependent on the normalization of the chiral ring generator, but these dependencies cancel out in the double difference observables, Z sub n plus 1, Z sub n minus 1 over Zn squared. And then I'm defining these Q's to be the logs of the Z's. And so these are now scheme independent, and in principle, they can be evaluated straightforwardly as functions of J and alpha using Feynman diagrams in the effective theory with no further input from the underlying CFT, as long as we're talking about power law corrections in large J perturbation theory. So the expansion has the structure, these QNs, these logs of the 2-point functions have the form AN plus B plus J log J, where J is N delta, J log J plus alpha plus 1/2 log J plus a whole sum of power law corrections. And so these first two terms are scheme dependent and normalization dependent. The third term is the classical value of the source term, the one loop free term, and the classical anomaly term contributions. And the last are the power law corrections. And the structure of the EFT makes it clear that these power law corrections are polynomials in alpha, where the polynomial is of order m plus 1, where m is the negative power of J. And that can be just seen from the structure of the Feynman diagrams of the effective theory. So of course, directly evaluating multi-loop diagrams in the EFT is hard. So to evaluate power law corrections, my collaborators and I just used a series of tricks: direct evaluation of some low order diagrams, use of known data for some theories like free theories and n equals 4, supersymmetric recursion relations, and embedding of Coulomb branch EFT into some non-unitary UV completions, using ghost hypers, some sort of slick superconformally invariant regulator for these n equals 2 theories. So with this combination of tricks, we were able to solve all the power law corrections for any value of alpha, with the result that these logs of the 2-point functions are an plus b plus log of the gamma function of j plus alpha plus 1, where j is 2n and alpha is the anomaly coefficient, and then exponentially small corrections, which are outside the domain of the EFT, but they are the subject of the second half of my talk. So I'll comment on those after the break. So this is a good time to break.
Okay, great. So let's pause the recording.
Oops, let me find
it's to Kola.
No, it's not to me. I'm not the one recording.
Oops, I think maybe I have to stop sharing to do that. That's okay. I'll do it.
Well, I think just pause.
Yeah, I can stop.
The bottom line.
Wait, I don't understand.
Yeah, there is a.
I can't tell if it's recording or not. I just pressed it.
Is it me who is recording? It's me who is recording. Okay, sorry.
Okay.
Yeah, please.
So, okay, so we have this nice explicit formula up to exponentially small corrections, and I'll comment on those in a moment. But before I do, I want to just open up the subject of confirmation of these large charge predictions in general for bosonic and supersymmetric theories, confirmation by sort of other means. So starting again with the O2 model, where we had this leading asymptotic expansion, this j to the 3/2 plus j to the 1/2 minus universal j to the 0 term, it would be good to compare with Bootstrap. There, unfortunately, for the O2 model, with charged operators, there isn't a huge amount of bootstrap high precision bootstrap work. There is some. But the first really non-trivial confirmation came from a Monte Carlo analysis up to j = 15 in the O2 model. So these results are from a PRL by Banerjee, Orlando, and Chandrasekaran from a few years ago. The theory curve is the curve, the Monte Carlo data are the boxes, and the error bars are too small to see. And the theory curve, which is made with the first 3 terms in the expansion, just goes right through every data point, even at low j. So that's unexpected. The large j expansion seems to be extremely accurate, even quite far outside what you would expect to be its regime of validity. One can compare with Bootstrap. So Bootstrap has somewhat precise data at j = 2, and there's extremely good overlap between Monte Carlo with large j fit with Monte Carlo data, and Bootstrap. So they agreed to 4 significant digits. Moving beyond the O2 case to other models in the same large charge universality class with the grad chi cubed effective action, there was an analysis done by Anton de la Fuente about 3 years ago, a large topological charge in the CPN models. So the CPN models in 3 dimensions all have a topological charge coming from winding on the holomorphic 1 cycle, complex, 2 cycle, complex 1 cycle in the complex curve in the CPN, and combining large N methods with machine learning methods to calculate some determinants. This large J expansion was worked out, and the j⁵ halves and j⁴ halves coefficients are dependent on the n of the CPN model, but then the c⁻⁴ term is not, and it matches this universal prediction matches what was calculated by De La Fuente up to 1 part in about, or 3 parts in 3 parts in 1,000. Okay, so moving on to predictions for the d = 4 n = 2 superconformal theories with 1-dimensional Coulomb branch. So for the case of the free abelian gauge theory and the n = 4 super Yang-Mills theory with gauge group SU2, our all orders in J power law formula agrees with the exact expression exactly, with no correction.
Sorry, just I don't know, maybe I already moving towards the next thing. This constant, you know it analytically, right? Because it's one loop for you.
That's right. That's right. So this EFT prediction is analytic. I mean, every digit can be worked out in principle. In De La Fuente's calculation in the CPN models, this was a numerical calculation in a combination of large N methods with numerical methods.
It's not some known constant like zeta3 or Catalan number or something like
that. I think it is a determinant. It's a renormalized determinant that may be calculable analytically, but I think it hasn't been.
All right. Okay.
So I mean, I think and that's true, by the way, of a couple of other of these large charge things that have been done, for instance, by Jambi and Hyman. I think there are determinants which possibly in principle could be computed analytically, but haven't yet been.
Thanks.
So for other cases, okay, so right. So for the first 2 cases in n = 2, these correlation functions, those can be computed analytically, and they just match with the large charge prediction exactly, with no exponential corrections. So for n equals 2 super QCD, we've been able to compute up to, well, so initially, a few years ago, we were able to compute up to about charge 76, just by numerically running a localization algorithm that was invented. The algorithm for computing by localization was invented by Komargatsky, Gomis, Gershkovitz, and those three. And now you can see even at that level, the theory curve matches the localization data pretty well. Now, again, we had to compute these double differences to get rid of the non-universal coefficients that were linear and constant in the log of the correlator. But you know, there are some small differences, and we wanted to try to understand the disagreement between the all orders formula and the exact localization results. So the framework for large J analysis dictates that any disagreement should be smaller than any power of J and should be associated with a breakdown of the Coulomb branch effective theory. And the natural candidate for such an effect would be the propagation of a massive particle over the infrared scale. So we would expect the leading difference between the localization result and the EFT prediction to be something like some constant, or maybe a power law, times exponential of e to the minus mass of the BPS particle times the infrared scale, which would be the radius of the sphere. So that would be, the exponential would be e to the minus some constant times square root of J over m tau. So we compared the difference between the EFT and the exact results in a certain scaling limit, this double scaling limit I mentioned before, where the coupling is being taken weak, the charge is being taken large, and the ratio is fixed. In that limit, we compared the difference between the EFT and the exact results computed by localization with this exponent held fixed. And we wanted to just numerically fit that difference with this supposed virtual BPS dion ansatz for the exponentially small correction. So we found that the difference fit pretty well to about 1.6 times e to the minus 1/2 root pi lambda, where lambda was 2 pi j over m tau. Turned out that this number was not quite right. It was a little bit off, but you know, that exponential ansatz, even with the exponent slightly off, fits the data just extraordinarily well. This data is the difference between the EFT prediction and the localization result. So with the dominant universal EFT stuff subtracted out completely. And that difference just fits this exponential ansatz with extraordinary accuracy, even at rather lowish values of the R charge.
But this EFT series is asymptotic series, probably. No?
Well, the EFT term is resummed. I mean, the EFT term is just the log of a gamma function, right? The EFT contribution is just that.
Ah, okay. So it's resummed. Okay, I see.
Yeah.
Yeah, good.
It has like a canonical resummation.
Yeah. Mm-hmm.
Yeah. Okay, so we saw the large quantum number expansion gives an asymptotic expansion that's sort of complementary to ordinary perturbation theory. It can be applied to all sorts of things. Okay, anyway, I'm just summarizing things I just said. This is a rather interesting situation. So due to the magic of supersymmetry, not only can we compute all power law corrections exactly modulo the scheme-dependent coefficients, we actually are able to compare to exact results to a precision where we can see the qualitative breakdown of the effective theory that we use to generate the all orders approximation. So seeing that, one is naturally tempted to try to go further and compare the exponentially small corrections with physical expectations at a precision level as well. So in order to do this, one has to really take on these non-universal coefficients A and B, which in particular, well, they're scheme dependent and they're normalization dependent, and they depend on the marginal coupling, so they're kind of complicated. But you have to first say figure out what those are, because the sum rules are fine for checking power law corrections where all three adjacent terms in the sum have about the same magnitude. But for the exponentially small corrections, the three terms in the sum don't have quite the same magnitude. So really, the sum rule, taking the sum rule introduces a lot of imprecision. So we'd like to work out what A and B are. So they're not only dependent on the marginal parameter, they're also scheme dependent. So they're scheme dependent, but they're not inherently ambiguous. Having a scheme dependent coefficient in a microscopic or effective Lagrangian just means you have to be careful about how operationally you're defining your renormalized Lagrangian parameters relative to the UV completion or to the renormalization procedure being used. So for generic theories with marginal parameters, that's often a bit involved, but with extended supersymmetry, the scheme dependence can often be reduced to an ambiguity by a holomorphic function of the complex coupling constant. And for theories like SQCD, which have an S-duality symmetry, even the holomorphic ambiguity can be reduced to a finite parameter, which can be eliminated altogether by matching with perturbation theory. So that's the course I'm going to take here to match these A and B coefficients. So the first scheme dependence to discuss is the A coefficient. So it's a kind of classical scheme dependence having to do with the parametrization of the holomorphic gauge coupling. The Coulomb branch chiral primary is uniquely defined up to an overall normalization characterized by its supersymmetry properties and by its dimension and its R charge. The overall normalization is exactly what matters, so we have to specify it. So in the literature, the way mostly used to normalize curly O is by its relation to the marginal operator. So one can write curly O can be thought of as the n equals 2 f-term superspace integrand over all four positively R-charged Grossman coordinates to generate the holomorphic half of the marginal operator that adjusts the gauge coupling. So in other words, this chiral ring generator integrated over chiral superspace gives some constant times trace of the self-dual part of the field strength squared. So the normalization of O is related to the normalization of the dimension 2 chiral primary that's linked to the normalization of the marginal operator that's the superconformal descendant in the same multiplet. But this doesn't resolve the question because a marginal operator itself doesn't have a universal natural normalization. Rather, the chiral half of a complex marginal operator transforms under reparameterizations of the coupling constant as a section of the holomorphic cotangent bundle over theory space. So in other words, it transforms as d tau prime over d tau, a holomorphic Jacobian of the coupling, where m is the marginal operator. And the chiral primary curly O has exactly the same transformation because it's canonically related by supersymmetry. So curly O transforms with that same holomorphic Jacobian under a holomorphic reparameterization of the coupling. So under this coupling reparameterization, the exponentiated A coefficient transforms as the norm squared of the chiral primary itself. So we'll exploit this transformation law to solve for A in a particularly simple holomorphic coordinate, and then write the transformation law in any other holomorphic coordinate, including the natural Lagrangian parameter tau. So there's a second, less obvious scheme ambiguity related to the Euler density counterterm. So first of all, it's very non-obvious why this counterterm should even be relevant at all for the computation of two-point functions, but some elementary deduction shows that it is, because two-point functions on flat space are conformally equivalent to two-point functions on the four sphere, and the four sphere has non-zero Euler number. So the sphere partition function transforms multiplicatively under an additive shift of the coefficient of the Euler counterterm. And supersymmetry does allow the Euler counterterm to appear in the action, but it's in some sense an n equals 2 f term, so it can appear only with a holomorphic plus anti-holomorphic dependence on the holomorphic gauge coupling. And since these z sub n are actually the unnormalized partition functions with sources, they're affected by the same counterterm ambiguity as the sphere partition function without sources. So this b coefficient is the n to the 0 term in the large n expansion of q sub n. So e to the b transforms with the same Euler counterterm ambiguity as the sphere partition function. So e to the b transforms as the norm squared of a holomorphic function times itself under an Euler counterterm shift. So fixing the scheme ambiguities is greatly simplified in a theory with an S duality. So in terms of the exponentiated gauge coupling, Q is e to the 2 pi I tau. The S duality symmetry acts in this way. It acts by fractional linear transformations on Q. S acts as Q goes to 1 minus Q. T acts as Q goes to Q over Q minus 1. It's not quite the same fractional linear transformation by which S duality acts in n equals 4 super Yang-Mills. So the infrared abelian gauge coupling, sigma, is the one that transforms in the familiar way. The infrared effective gauge coupling transforms as A sigma plus B over C sigma plus D for an SL2Z transformation. And the relationship between the IR and the UV gauge coupling is given by the so-called modular lambda function. And that relationship was actually worked out by various people. It was made sort of clarified the most geometrically by work by Gayoto and by Alde Gayoto and Tachikawa. So given our transformation law for coupling reparameterizations, we can take modular transformations as a special case. And it follows that the chiral marginal operator, M, in the frame sigma, and the chiral primary curly O sub sigma transform as holomorphic modular forms of weight 2. And from there, we can see that the A coefficient transforms as a non-holomorphic modular form of weights 2, 2. So the next ingredient is the recursion relations discovered by Papademos as a generalization of the TT star equations to D equals 4. And those say, so these Q sub n's, the logs of the correlation functions, obey the equation, the so-called Toda chain equation, Laplacian with respect to sigma on Q sub n equals e to the Q sub n plus 1 minus Q sub n minus same thing shifted down by 1. So when applied to the power law corrections, they uniquely fix the form of Q sub n to be the gamma function, gamma 2n plus 5 halves, as we saw, up to the terms an plus b. But they also give equations for the coupling dependence of the A and B terms. So for the A term, they give this equation, which is the Liouville equation. And for the B function, they just say that the difference between B and A has to be harmonic. Okay, and these are covariant under both the holomorphic reparameterization dependence, scheme dependence, and under the other scheme dependence, this Euler counterterm shift. So that means we can solve these equations in any scheme we like and transform to any other scheme we like. So it's simplest to solve in this infrared gauge coupling coordinate, sigma. So in the sigma coordinate, the Liouville equation, the modular property, and the correct match with the tree level double-scaled perturbation theory uniquely fix the result to be e to the A coefficient is 16 over m sigma squared. So to specify the Euler counterterm scheme choice, we will compare with the scheme in which the sphere partition function was originally calculated by Peston using the U2 instanton partition function as computed by Nekrasov. So the partition function as computed in this scheme has a duality transformation. That's the way we're going to characterize this scheme. In that scheme, it can be shown to have this duality transformation under the S transformation here and under the T transformation here. It transforms by these norm squareds of simple rational functions of Q. And I say derivable because it didn't seem to have been, we couldn't find it written down anywhere in the literature. In order to find it, we had to transform to AGT's scheme. Anyway, I don't want to eat up too much time by talking about how we did that. It was just by carefully matching scheme dependencies in the literature and identifying scheme choices by their duality transformation properties. So with that transformation law for the B coefficient in the Peston-Nekrasov scheme, the general constraint from the recursion relations, we have e to the b is some holomorphic function squared times e to the a. That gives the solution e to the b in the Peston-Nekrasov scheme is some constant, some coupling independent number times modular lambda function absolute value to the 2/3 times 1 minus modular lambda function absolute value to the 8/3 over dedicant eta function of sigma to the 8 absolute value im sigma squared. Just worked out using, the recursion relations, the duality properties, and keeping careful track of the scheme dependencies. So again, we have an ambiguity by a coupling independent constant, which again, we fix by matching with double-scaled perturbation theory. And this time it's simpler to match a strong double-scaled coupling. We could have done either, by the way. But it was easiest because we could make use of the exact solution to the one-loop double-scaled coupling dependence found by Grassi, Komargodski, and Taizano. So we found that the result is e to the b in the Peston-Nekrasov scheme is glacier gamma to the 12th power times e to the -1 times 2 to the -9/2 times pi to the -3/2 times this same quantity I quoted. I'm not going to speak it again. That was the solution for e to the a coefficient. So having in hand the explicit expressions for the A and B coefficients, we can now compare the full EFT approximation at large R charge with expectations from localization without taking these double differences that introduce extra numerical imprecision. So it improves the numerical accuracy of the match at basically all values of tau to the point where the error in making the EFT approximation compared to the exact result has to be exaggerated on a plot in order to be visible at all. So at this point, we really began to have trouble conveying the accuracy of the expansion visually because it was almost impossible to make the difference between the exact result and the EFT approximation large enough to even see. So this plot was done by Domenico Orlando, basically plotting the EFT approximation against the localization results for various values of tau and n, and then magnifying a portion of it where the approximation is the least accurate because the values of n are the smallest, and blowing it up, magnifying it so that you can just barely with the naked eye make out the difference between the EFT approximation and the exact result from localization. Okay. And then, yeah, so this was at the curves were a fixed n and as functions of tau, and then here the curves are at fixed tau and as functions of n, and in each case you have to really magnify the data where they're least accurate to even see anything at all in terms of a difference between the EFT approximation and the localization result. And even there, as soon as n gets a little bit large, you can barely make it out. So now we've solved for the full EFT approximation to the correlation functions up to these exponentially small corrections, which we'll call massive macroscopic propagation corrections, because these exponentially small terms are describing the massive macroscopic propagation of virtual BPS particles. And so finally, we'd like to get a handle on these two by the same kind of strategy, use the same ingredients, recursion relations and EFT inputs. So here's how we do it. We use the fact that the connected MMP term is exactly what's left over when we take the full connected partition function with sources, so log of z sub n, and subtract the connected EFT contribution for which we now have the exact formula. So we take these exact q sub n's as computed by localization, and then subtract off this exact EFT formula, and what we're left with should be these massive macroscopic propagation corrections. So now, using this identity, this kind of definition for the MMP terms, we can rewrite the recursion relations for the full connected amplitude with sources as a recursion relation for the MMP terms by themselves. And the recursion relation we get is like this. We get left-hand side equals right-hand side, where left-hand side is 16 m sigma squared times partial sigma bar of the MMP term. And the right-hand side is 2n plus 7 halves, 2n plus 5 halves, z MMP sub n plus 1 over z MMP sub n minus 1, where z MMP is the exponential of q MMP. And then minus the same thing shifted down by 1, by n shifted down by 1. So the recursion relation is one input, and the next input is the structure of the asymptotic expansion as dictated by effective field theoretic considerations. So to understand the structure of the expansion, we have to think carefully about what it is the MMP corrections represent. So mathematically, they're the sum of all connected diagrams minus the EFT contributions, with the latter representing the propagation of virtual massless particles together with the microscopic propagation of massive particles, which are absorbed into effective couplings of the EFT. So after those are subtracted, we're left with connected diagrams which each have at least one macroscopic propagator for a massive particle. Now, the lightest massive particle is the doublet hypermultiplet. And in terms of the R charge and gauge coupling, its mass is given by 1 over r, r is the radius of the sphere, times root of 2n over pi m sigma. So it's the infrared gauge coupling, by the way, that enters the BPS bound. So remember, we're always working in this limit where the infrared scale is much less than the UV scale. So at fixed, sorry, this gallery is hiding my text here. At fixed coupling and large R charge, the mass of the hyper is parametrically above the cutoff. Now, there's nothing inconsistent about including heavy particles above the cutoff in effective field theory, as long as we do so consistently. And actually, such treatments of super cutoff objects in EFT are in principle well understood. They're familiar in many contexts where the heavy state is stable. So examples include the heavy quark effective theory, effective string theory, the D-brane action, gapped goldstones, many other examples. And these examples can all be described in terms of a second quantized Hilbert space for light fields coupled to a first quantized dynamics of motions of the heavy particle. So that's the kind of EFT calculation we're talking about here. So as long as large R charge is a semi-classical limit, we expect the leading contribution of the virtual massive particle at large R charge to come from a classical configuration of the action for a massive BPS particle coupled to a massless vector multiplet. And the heavy particle is still conformal. It gets its mass strictly from the magnitude of the VEV of the vector multiplet, which is constant in the conformal frame of the cylinder. So we have to look for finite action classical trajectories of a particle of constant mass on the cylinder. And that narrows it down a lot because there aren't very many finite action trajectories for a massive hyper on the cylinder. In fact, the only such trajectories are the great circles of the spatial S3 at fixed value of the radial time coordinate. So they just look like this: geodesics wrapping an equator of the S3 spatial slice. And that means that the MMP function has the asymptotic expansion at fixed coupling and large charge that's of the form Q sub n is e to the minus Gothic W, where Gothic W is the world line instanton action with terms that are parametrically smaller in n coming from quantum fluctuations of the fields and of the world line trajectory. So using the BPS mass formula, we find that the world line instanton action is root 8 pi n over m sigma, And the first subleading correction is given by the quantum fluctuation determinant of its geometric world line action about the classical trajectory. And that contributes to Gothic W proportional to log n. So there are all sorts of higher derivative classical terms and quantum back reaction and so on. And these contribute to Gothic W with with negative powers of n. So incorporating all those fluctuations gives an asymptotic series for Gothic W, which is the negative log of the log of z sub n, which goes like this: root 8 pi n over m sigma plus gamma of sigma log n plus a sigma dependent series of corrections times n to the minus p over 2 with p a positive integer. So at this point, again, in principle, we could calculate all these terms directly in the effective theory of geometric fluctuations of a massive world line coupled to massless fields in the bulk with a non-trivial classical solution. But you have to do no calculation at all, basically, because the recursion relations give PDEs for the sigma dependence of all of these functions at each order. And it turns out we have enough information about boundary conditions to find the physically correct solution to each PDE. So for instance, the recursion relation at order log n says that gamma depends only on the real part of sigma. And the real part of sigma is the infrared theta angle. But the dynamics must be independent of the infrared theta angle at weak coupling, because the infrared theta angle enters only through instanton corrections. So sigma must be independent of, gamma must be independent of sigma identically. To find the actual value of gamma, we must match with double-scaled perturbation theory as computed by GKT. So taking the double scaling limit of Gothic W and then taking the strong coupling expansion of that double scaling limit shows that gamma has to be equal to negative 1/4. So the functions, these higher corrections can be found similarly. At each p, the recursion relations give us a first order PDE for sigma. Then the boundary condition at weak coupling forces the correct solution to depend only on the imaginary part of sigma. And then that determines the solution up to a single sigma independent constant. And that constant can be fixed by matching with double scaled perturbation theory as computed by Grassi, Kamargatsky, and Taizano. So the first few terms I just write down here. So S is the imaginary part of sigma. So W1, the coefficient of the n to the minus 1/2 term in Gothic W, is like this. It's some polynomial in the square, some rational function in the square root of S. W2 is another one like that. W3 has more terms, and so forth. And you can compute algorithmically at each order. W4, they get longer and more complicated at each order, but they're always computable. And so now I'm going to show you the accuracy. And again, the difficulty is just showing, estimating the error and seeing it visually when it's almost impossible to see the error visually. So to do it, instead of plotting theory against data, that's hopeless. You can't see any difference at all, no matter how you blow it up. Plotting theory against data, what I did was to take the difference between the exact MMP correction as computed from localization and the estimate, dividing by the exact MMP correction, taking the absolute value of that, taking the log of that, and then taking negative 1 over log 10 times that. So in other words, the thing that I'm plotting is actually the effective number of significant digits with which up to which the exact MMP formula, the exact MMP correction as computed from localization matches the next to next to next to next to next to next to leading order estimate for the MMP function, and plotted up to about n equals 150. So you can see at n equals 150, the agreement is of the MMP functions themselves, not even the whole amplitude, of just the exponentially small correction agrees with the estimate for it up to more than 8 significant digits at next to next to next to next to next to next to leading approximation.
So the coefficient of this expansion, are they going getting smaller or?
Oh, very good question. Very good question. The asymptotics, I don't know, and I would really like to know. There are interesting questions having to do with resurgence and the breakdown of the asymptotic series. What I will say is that at this order, there's no sign of a breakdown of the asymptotic series.
But still asymptotic series, you expect, of course, right?
Probably, but there are confusing issues to do with the way supersymmetric asymptotic series behave versus the way generic ones behave. And that has to do with like the zero mode, the existence of zero modes on the instanton that would control the breakdown of the asymptotic series by resurgence theory. For BPS quantities, the behavior is a little bit different than generic resurgence theory would predict. And this is a kind of confusing issue. So I can't
but
say
at least up to 6th order, it looks like factorially decaying or something like that.
At 6th order, you're not nearly close enough to the breakdown, to the order at which you would expect it to break down. I mean, you would expect it to break down at an order, comparable to the R charge, and the R charge is like 150. But I only computed up. I only computed
depends on some parameter. There is some parameter for which it gets worse, right?
No, it's a large charge expansion. So the
so
parameter is the R charge itself. Oh, right. Yeah. So you could go exactly. So you can make the R charge not so big, and you could ask about whether the asymptotic series is breaking down, like down here. Yeah, you're right. You could ask that. You could maybe test it. Yeah, it's a good question. It's a good question. I would like to know the answer to that, and I sort of thought about it a bit, and it's inconclusive at the moment.
Thanks.
Yep. And yeah, even though I didn't talk about this, you can also compute higher corrections to the double scaling limit, loop corrections to the double scaling limit, again, using the recursion relations. And again, you get these phenomenally accurate estimates for the MMP function. The difference is that in the for the double scaled expressions, at a fixed order of accuracy, they get slightly worse very slowly as you go larger in n, because we're really computing at ultra large n and fixed coupling, which is not quite consistent with the regime of validity of the double scaling limit. So when you go to ultra large n, any given order of the expansion begins to deteriorate a bit. But
so what are the spikes? Are this just when accidentally approximation is exactly the same? It's just like oscillating around the exact solution, the approximation.
Yeah, that's right. The spikes are the accidental agreements. Right. That's right. Yeah, and you have a couple of them here too. Yeah, that's when the difference between the exact answer and the estimate goes from like negative to positive. And then here's a table of actual data. You can see for even for some low values of the R charge, the next to next leading order estimate is like still very good. For R charge 10, the agreement is 0.0469 versus 0.0470, and then once you go up to the highest, not even the highest values, just like 120, the estimate is 0.0000197108256 versus 10197108872, or like at 120 it's 10 to the minus 6 times 5.8809799426 versus 5.8809811146. And remember, these are this is the agreement between theory and data for the exponentially small correction to the full correlate, to the log of the full correlator. The logs of the full correlators themselves agree to 17 significant digits up at these large values of the arbitrage. So okay, so
so this is again, so that's for 2-point function, right?
This is for 2-point functions, yeah.
And then is it something special about 2-point function, why it works so well? Say if you consider excitations around, is it still?
If you consider like non-BPS,
well,
yeah,
of course you can compare them with localization, but
right. That's the hard part. You don't know how to compare them. There may be bootstrap ways of doing comparisons. People haven't worked out, bootstrap methods for near extremal correlators, but I have a feeling bootstrap should have something to say about that. There should be a bootstrap method that's well adapted to that, I think, but I think we don't have it.
Anyway, you wouldn't get 17 digits probably to compare with.
Probably not, but who knows, I think, large quantum number aside, this is a very exciting time in quantum field theory in general, because it's a time when many different methods are beginning to, for certain types of correlators, many different methods are beginning to converge. Integrability, localization, resurgence, bootstrap, EFT, large quantum number of various kinds, now are gaining the ability to talk about the same observables and really begin to be tested against each other. And so, in the bigger picture, I think this is a really exciting time in the field of quantum field theory in general. And who knows? I'm hoping that these kind of predictions will stimulate further, ambitions of people to develop other methods to probe these same regimes, with hope of getting like precision tests of new methods. So I'll conclude by saying the large J expansion gives an analytically controlled way to compute CFT data outside of any other sort of simplifying limit, particularly illuminating simple behavior in regimes where numerical bootstrap methods can't currently access. The large J predictions in cases like the O2 model and various superconformal theories with one-dimensional Coulomb branch agree extremely well, even at low J, with things like Monte Carlo, Bootstrap, and exact supersymmetric methods. These results have greatly improved our control and conceptual understanding of even the simplest strongly coupled CFT, and I hope that the analysis of more examples will yield further interesting surprises about the large-scale structure of theory space. So thank you all.
Yeah,
thank you.
Okay, there were many questions already, so maybe some want to ask further.
Yeah, maybe for those who will be watching it in recording, they can address the questions by mail, I guess.
Yeah, sure. I'm always happy to talk.
Just due to unusual time, I think we lost a few confused people.
Yes.
Almost including me.
Simon, since you are here, let me just ask a very specific question. The formula for the large G for O3 model and O2 model, for O3, it still contains like the two leading terms and the constant is C.
Right. Yeah, O3 and O2, it's interesting. They're the same. in some sense the same large J universality class, in the sense that the massless stuff is the same. The difference is, so that doesn't mean that the asymptotic expansion is the same, because the non-universal coefficients will be different between the two.
Right.
But the universal term will be the same. But the universality class in the O3 model is in some sense has more to it, because there's also a massive particle, a so-called massive Goldstone. So there's this whole story as developed by Moriyama, Browner, Watanabe, about situations in which you have Goldstone's theorem, where the extension of Goldstone's theorem predicts massive states with very specific masses and specific couplings of some sort. And the third degree of freedom of the O3 model is a massive Goldstone in that sense, coupled to the massless sector of the O2 model. And
okay, and they contribute to high order.
Well, no, in some sense they don't, in the sense that you can integrate out the massive. There's a theory without the massive Goldstone you can talk about just in its own right, and it is in the exact same universality class as the O2 model. But then there's this extended theory you can also talk about. So there are kind of two layers to it. So the higher ON models have these sort of two layers with and without the massive Goldstones. And there was a very nice paper by the EPFL group, Bertazzi and Cuomo and some other people, called something and gapped Goldstones. Anyway, they sort of talk about these two layers a bit.
I see.
And also, the original paper by on the ON models at large charge by Orlando Reffert, Lucas, and Alvarez Gomez also sort of works out the spectrum of those models and so on, including the massive Goldstones.
I see. Okay, I'll take a look. Thank you.
You're welcome.
There are more questions? If not, I can ask some technical one. So from this effective field theory, you computed by the summation this gamma function.
That's right.
Is it, did you like just guess it and check up to high order, or?
No, in fact, we didn't know it was a gamma function until like the last minute. We'd worked out, we had worked out, we didn't even know it was coupling independent until fairly late in the game. We really kind of did it the hard way. Well, the hardest way would have been actually working out Feynman diagrams, but we did it like the next hardest way after that, which was working out the first three orders of Feynman diagrams and then using the recursion relations from there to work out all the rest.
So you used this as initial data for recursion.
That's right. So we used, so specifically for the recursion relations, you need the first three orders. And one of those is like a 2-loop calculation. But then we realized we could read off the exact answers from two theories where the exact answers were known, and then calculate a tree diagram for the third linearly independent term. So that's what we did. And then we used those three as initial data for the recursion relations, calculated all the all the higher terms, and then at the last, there were some Bernoulli numbers or something, and then Domenico Orlando noticed that they were resumming to a gamma function. So yeah, we definitely didn't just guess it and check.
I see. All right, I think we can thank Simon again and close the official part at least. Thank you.
Thank you so much for the invitation. It was really fun.
Yeah, sorry for an unusual time. It's a bit normally even more fun, but anyway, thank you for the nice talk, and I will stop recording now.
Okay, thank you again.